Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Hello everyone. It's great to have you here as we delve into the fascinating world of adaptive Bayesian optimization for high-precision motion systems. To set the stage, could you explain the importance of controller, tuning, and parameter optimization in the context of closed-loop systems, particularly in high-precision applications?
Controller tuning and parameter optimization are like adjusting the settings on a video game controller to make sure your character moves smoothly and accurately in closed-loop systems, which are systems that constantly check and adjust their performance based on feedback. Getting these settings just right is crucial, especially for high-precision applications like semiconductor manufacturing. When we fine-tune a controller, we are ensuring that the system can respond quickly and correctly to any changes, like a car adjusting its speed based on the road conditions. In high-precision motion systems, this means making sure that movements are precise and any vibrations or disturbances are minimized, similar to making sure a toy car goes straight without wobbling. Bayesian optimization, which is a smart way to find the best settings, helps in this process. However, it can be slow, like trying to find a hidden treasure by searching every inch of a big area. To address this, the proposed methods aim to speed up the optimization process while maintaining stability and ensuring safety, which is crucial when working with expensive and sensitive equipment. In summary, proper controller, tuning, and parameter optimization help achieve the best performance and accuracy in closed-loop systems, making them vital for tasks that require high precision.
That's a great analogy for understanding the significance of controller, tuning, and parameter optimization in closed-loop systems. Now, could you elaborate on the challenges associated with traditional Bayesian optimization methods, particularly regarding their computational expense, and how these challenges impact real-time applications in high-precision motion systems?
Traditional Bayesian optimization methods are like having a really big map to find hidden treasure, but it takes a long time to look at every possible spot. This method is very effective in tuning controllers, but can be computationally expensive, meaning it requires a lot of time and resources to find the best settings. In high-precision motion systems, where every tiny adjustment matters, this slow process can be a problem. Imagine trying to change the speed of a racing car while it's speeding around a track. If your adjustments take too long, the car might not respond in time, leading to poor performance or even accidents. The computational expense of traditional Bayesian optimization can make it hard to use in real-time situations where quick adjustments are necessary. If the system experiences any disturbances, such as vibrations or changes in load, the controller needs to adapt immediately to maintain stability and precision. However, the slow nature of traditional methods could result in instability, just like trying to steer a boat while you're still figuring out its speed and direction. To tackle these challenges, new approaches are being developed that focus on being data-driven and more efficient, allowing for online tuning of controller parameters without the heavy computational load. This way, high-precision systems can quickly adapt while ensuring performance and safety, crucial for industries like semiconductor manufacturing, where precision is key.
That illustrates the challenges quite well. The need for efficiency in real-time applications is certainly paramount. Can you explain how the proposed method in the study addresses these computational challenges, particularly through the modifications made to the GoOSE algorithm for parallelization and computational efficiency?
The proposed method addresses computational challenges by enhancing the GoOSE algorithm, making it more efficient and capable of operating in real-time situations. Imagine trying to bake a large batch of cookies. Instead of using just one oven, which can take a long time, you decide to use multiple ovens at once. This is similar to how the modifications facilitate parallelization, allowing the algorithm to perform multiple tasks simultaneously. In the modified GoOSE algorithm, there are two key strategies introduced: paraGoOSE and lookup GoOSE. paraGoOSE is like having several chefs working on different tasks in a kitchen. It runs multiple optimization processes at the same time. which helps speed up finding the best controller settings. Each process works on a different set of tasks, and they share the workload, making the overall process more efficient. On the other hand, lookup GoOSE optimizes for the entire task grid when switching phases, but it is more computationally expensive compared to ParaGoOSE. While both methods aim to maintain safety and stability, ParaGoOSE is designed to be quicker and requires less computational power, enabling faster adjustments to be made in real time. By using these parallel processes, the modified GoOSE algorithm can keep pace with the changes required in high-precision motion systems, similar to how multiple people can complete a cooking task faster than just one. This means that the system can adapt quickly to disturbances or changes in conditions, ensuring optimal performance when it matters most.
That's an insightful explanation of the algorithm's enhancements. The analogy of using multiple ovens certainly clarifies how parallelization boosts efficiency. Now, could you discuss how the performance of this new method was evaluated in practical scenarios, particularly focusing on its application in real industrial motion systems and the criteria used for comparison against traditional methods?
The performance of the new method was evaluated in practical scenarios by applying it to a real precision motion system used in the semiconductor industry. This evaluation is like testing a new recipe in a bustling restaurant to see how well it works with actual customers. To assess the method's effectiveness, the researchers modified factors such as the payload, the weight being moved, and the reference step size, how far the system moves with each command. This is similar to changing the ingredients and cooking times in a recipe to see how the dish turns out under different conditions. The performance of the new approach was compared against a traditional method based on interpolated constrained optimization. They looked at how well each method could handle the requirements of high-precision tasks, ensuring that safety and operational constraints were maintained throughout the process. This is akin to making sure that a new dish not only tastes good, but also meets dietary restrictions. The results were measured through different criteria, such as how accurately the system could position itself during operation, and how quickly it could adapt to changes in conditions. By using multiple parallel processes, the new method aimed to achieve better real-time performance, allowing for quick adjustments and maintaining high precision, which is crucial in industrial applications. Overall, this practical evaluation helped to demonstrate the method's suitability for real-world use, validating its advantages over traditional techniques.
That's a fantastic way to illustrate the evaluation process. It highlights the practical implications of the method effectively. Finally, could you summarize the key contributions of this research to the field of adaptive Bayesian optimization for high-precision motion systems and discuss its potential impact on industrial applications?
The key contributions of this research to the field of adaptive Bayesian optimization for high-precision motion systems include the development of an efficient, data-driven algorithm designed for real-time applications. It's like creating a high-performance sports car that can adapt quickly to the road conditions, ensuring a smooth and safe ride. Firstly, the research introduces a safe and adaptive control algorithm that utilizes parallelization through multiprocessing. This means that the algorithm can work on multiple tasks at once, enhancing its responsiveness and efficiency. By separating the optimization process into active and passive phases, it becomes more flexible and can adapt to changing conditions, much like a driver adjusting their speed based on traffic. Secondly, the researchers improved the GoOSE algorithm by making it computationally efficient. By removing the need for discretizing the domain, they streamlined the optimization process. This is akin to simplifying a recipe to make cooking quicker and easier without sacrificing flavor. Lastly, the effectiveness of this new method was demonstrated on a real precision motion system, which is essential in industries like semiconductor manufacturing. This showcases its practical applicability and reliability in high-stakes environments where performance and safety are critical. The potential impact of these contributions on industrial applications is significant. With the ability to adapt quickly and maintain high precision, this method can enhance the performance of various motion systems, ensuring they operate smoothly and efficiently. As industries increasingly rely on automation and precision, the findings from this research can lead to advancements in robotics and other areas where accurate motion control is paramount.
Thank you all for joining us today. We've discussed the importance of adaptive Bayesian optimization for fine-tuning controller parameters in closed-loop high-precision motion systems. Traditional methods face computational challenges, limiting real-time performance. Our researcher has presented a novel method that modifies the GoOSE algorithm for parallelization and efficiency, enabling it to handle real-time adjustment. This has been evaluated in practical scenarios, demonstrating its effectiveness in maintaining safety and precision. This research contributes to the field by developing an efficient algorithm that addresses challenges with traditional methods. It has the potential to enhance the performance of various industrial motion systems. Thank you again to our researcher and the audience for their participation.